Hello, this is part 3 of the lecture on spanning sets. So let's apply this theorem to, again, to come up with the set of vectors that have the property of spanning. That's what we would say. This set has the property of spanning exactly the null space of a matrix. So we want to find which are the members of this spanning set such that the span of that set is exactly equal to the null space. So what we're going after are the vectors we previously discussed as the z1, z2, z3, right? So we want to apply this theorem to come up with which are these vectors. Okay, and so here we have an example. This matrix has 6 columns and it has 5 rows. So this is a 5 by 6 matrix. We're interested on expressing the null space exactly as the span of some vectors. So what we do first is that we compute the RREF of this matrix, and this right away is telling us, remember, so in this case n is the number of columns here, so n equals 6 and r equals 3. Okay, in this case the set collecting the indices of dependent variables, set D, is 1, 2 and 4. On the other hand, the set that we call F collects the other indices. That's going to have the index 3 and then the index 5 and the index 6. Okay, so this is working with the original matrix. This is not the augmented matrix, and therefore had this been if we were instead augmenting this, right, this matrix would have not it wouldn't have 6 columns, so that we would say that n plus 1 would be 7. But so the number of columns here is 6, and that index 6 will be included in these calculations. Is what we call those indices correspond to the indices of free variables. So what we do next is that we use this information and we're gonna construct the z1, z2 in this case. This calculation n minus r equals 3 tells us that we'll have a vector z1, a vector z sub 2, and a vector z sub 3. So the set formed by these vectors is what we're calling the set S, right? And we want to construct each of those vectors. Each vector z sub j, each vector c sub j is an element of, that's where we have to remember. So here n has 6 entries, so each of these vectors is a member of C6. That means each vector c sub j has 6 elements, 6 locations, right? So there are 3 of such vectors. Here is indicated C1, C2, and C3. This is the first part that we read from that theorem. Each vector contains ones and zeros, and since we're working with these indices 3, 5, and 6, so the first vector is going to contain 1 on position 3 and zeros on position 5 and 6. We go to the next of the z vectors, is going to contain 1 on position, this is position 5, and it's going to contain zeros on the other positions, 3 and 6. And the last vector is going to contain a 1 position 6 and zeros on the other 2 positions corresponding to indices on the indices corresponding for free variables. So we have then filled in each of these vectors 3 positions, 3 locations with ones or zeros, and what comes next is to use the information from the RREF to fill in the other locations that appear this time. They appear empty, okay? And so we're going to use information, the set F contains indices 3, 5, and 6. Okay, so each of these indices is going to be key. So the column number 3 has entries 2, 1, 0, 0, 0, and so that will be the other piece of information. The theorem tells us take the negative negative of the entries on the RREF, and that's what we do next. So this vector z sub 1 contains now entries -2 and -1 precisely because those entries are coming out of this column number 3, one of the columns corresponding to the set of indices of free variables. The next vector uses information from entries that are stored on column 5, right? And so the numbers that appear listed here are exactly the negative of numbers on that column. And then the next vector is using information from the last column of this matrix of the RREF. And as you can see now, these vectors Z1, Z2, and Z3, they contain either ones or zeros or the negative of entries on the RREF of the matrix. So in summary, we say that we have succeeded here in finding such set, right? The set S is the set given by vectors Z1, Z2, and Z3, right? In fact, this set alone would be the set that contains these 3 vectors, okay? And so I would have to write here what each of those vectors is. So S is the set of vectors Z1, Z2, and Z3, expressed here as a set. That's what that would look like. However, what we have in the previous line is that is another way of saying what we're looking for is that we wanted to express the null space of the matrix as the span of a set S, right? So notice that here the notation may be a little convoluted, you're not used to, but this here is denoting that this is indeed the span of, right? So the set S is in the middle. When you write S, you have to write the braces and stuff, but this is another way of writing. Yeah, indeed, the null space of this matrix is exactly equal to the span of the set defined by these vectors, and those vectors were calculated by using the theorem S, S, and S. So in summary, we can say that the null space of the matrix is the span of this set. And one note is that while we're expressing the null space as the solution set of some homogeneous system of equations, we're directly using this theorem. It's a theorem that allows us to come up with the important thing about this illustration is the vector z1, the vector z2, and the vector z3.